the matrix 1001 called? The identity. You could have said the 2 by 2 identity, or I2. I think that's the notation your book uses for it. Or it's actually I2 by 2. Like that. True or false, a matrix equation and a vector equation can express the same information. True. They're just different notations for expressing a system of equations. All right, and what is the identity matrix times the vector 7, 9? 7, 9, yeah. That's the whole idea of the identity matrix. It's called the identity because it acts like the number 1 does in multiplication with real numbers. Gives you the thing back. And we're going to review multiplication of a matrix times a vector, but to multiply a matrix times a vector, to make sure that you can multiply them, you think about the dimensions. What are the dimensions of this first matrix? 2 by 2. 2 rows, 2 columns, so it's 2 by 2. And then what are the dimensions of that vector? 2 by 1. 2 rows, 1 column. So to know if you can multiply a matrix by a vector, or even a matrix by a matrix, which we'll learn later, the inner dimensions have to match, right? So the 2 and the 2 that are closest to each other, inner dimensions have to match. The result is going to be the outer dimensions, 2 by 1. So when we multiply these, my result is going to be a 2 by 1 matrix. 2 rows, 1 column. So I like to just kind of put like the general shape of the answer, so then you can fill it in. And then one way to think of multiplying a matrix times a vector is to think of doing the dot product of the row, first row times the first column. That goes in the first row, first column of your answer. So you take the dot product of 1, 0, and 7, 9. Anybody know what the dot product is? Yes, yeah. So I picture, like when I do this in my head, I picture taking this row of 1, 0, picking it up out of the board or off the paper, rotate it 90 degrees, and put it on top of the 7, 9. And then you multiply the things that land on top of each other and add the results. So you have 1 times 7 plus 0 times 9. Yeah, I just multiplied 1, 0, the row, times the column 7, 9. That's another way to think of it. You're going to get the same answer. Yep. I'll do it both ways. All right, so then you take the 0, 1 dot product with 7, 9, and you get 0 times 7 plus 1 times 9. And my final resulting vector is going to be 7, 9. And you didn't actually have to do all that work because you know that the identity times something gives you the something back. But the other way to multiply a matrix times a vector, and this is the way that your text emphasized, it said take each column of the matrix and multiply it by the 7 and the 9 as the weights. So you're going to take a linear combination of the columns, first column being 1, 0 with a weight of 7, second column 0, 1 with a weight of 9. So they emphasize multiplying a matrix times a vector as taking a linear combination of the columns of that matrix and with the entries in the vector as your weights. So this ends up being 7, 0 plus 0, 9, which is 7, 9. So you get the same thing either way. And you can use whichever method you like. Did you have a plus between them? Yeah. Like that? Yeah, that's wrong. Yeah, because that's a 2 by 2 matrix. The answer is a 2 by 1 vector. Okay, so just a reminder, for grading your reading score for today, 1 point for handing in a question, 1 point for each question you got right, 1 point if you took notes on the reading, maximum of 4 points. And we've lost the folders, so just make note of it on somewhere in your notes, and we'll add it to the folders when I find them. All right, so today's our third class, September 13th. We're going to finish lesson 4, which means we're going to start with the class activities from lesson 4. I already did the lecture part. We'll do that for about 30 minutes, and then we're going to do all of class 5, the demo portion and the activities portion. All right, so we are starting the group activities for class 4, which is page 23.
Yeah, before you start,
Okay, so today we're going to learn even more notation, which we were already struggling through some notation in the last activities. We're going to learn even more. And we're also going to be able to tell if a set of m by 1 vectors, or alternatively the set of columns of an m by n matrix, spans Rm. So we're going to be talking more about span. So several of you asked me to clarify span. We're going to talk about it again, and hopefully it'll get clearer each time we bring it up. Okay, so I have a system of linear equations, 2 equations, 3 unknowns. I want to write this as a vector equation. So we're just going to do some practice with translating notations here. So if I write this as a vector equation, I have my coefficients 3 and 1 with a weight of x1, coefficients 2 and -1, weight of x2, coefficients 7 and 1 with a weight of x3, and I ran out of room. That equals 5/8. So that's how I can translate that system to a vector equation. And you can just read the components across the top. This says 3x1 plus 2x2 plus 7x3 equals 5, and x1 minus x2 plus x3 equals 8. If I want to write it as a matrix equation, we have a matrix of coefficients, a whole matrix of coefficients. Instead of separate vectors, each of those vectors becomes a column. So I'm going to have 3, 1, 2, -1, and 7, 1. That's called the coefficient matrix. It holds all the coefficients of the variables. Then you multiply by a vector of weights, x1, x2, and x3. Because what this means, when we went over in the quiz, we said this notation means take each column of the matrix as a vector, and we're going to take a linear combination of those 3 vectors where x1, x2, and x3 are the weights. And that should equal 5/8. Yeah. Yep. So I would take this row 3, 2, 7, pick it up, turn it 90 degrees, put it on top of x1, x2, x3, and then you would multiply the things that line up and add them together. So you'd get 3x1 plus 2x2 plus 7x3, which is your first equation. Yep, I know. Yeah, it takes some getting used to. All right, if I wanted to write this system as an augmented matrix, that's what we've done the past 2 classes. We have the coefficients, 3, 1, 2, -1, and 7, 1, and we augment that with the 5/8, and that's the augmented matrix. So this is just 4 different ways of expressing the system of linear equations that I gave you. So the original way, then we have a vector equation, a matrix equation, and an augmented matrix. All are giving you the same information. And then how would you solve it? Yeah, use the augmented matrix and row reduce. All right, so if you remember from the reading, the product of an m by n matrix A and an n by 1 vector x produces an m by 1 vector AX. And that is the linear combination of the columns of A using the corresponding entries in X as weights. So I'm going to do each of these two ways, right? One the way the book emphasized and one with the 90-degree rotation. So I'll do the way the book said first. If I want to multiply this matrix times this vector, I like to think about the dimensions first. So what are the dimensions of this matrix? 3 by 2, 3 rows, 2 columns. What are the dimensions of the vector? 2 by 1, 2 rows, 1 column. So am I allowed to multiply these two together? Yes, because the inner dimensions match, right? The number of columns in the first thing equals the number of rows in the second. So the 2's match, I'm allowed to multiply them. What's the answer going to look like? What are the dimensions of the answer? Three by 1. The answer is going to have these outer dimensions, 3 by 1. Okay, so the book tells you that take a linear combination of the columns. So my columns are going to be 1, -3, and 1. And my weights are the -2 and the 3. So I put a weight of -2 on there. And then my other column is 2, 1, 6, and it's going to have a weight of 3. Linear combination of the columns of the matrix using the entries in the vector as the weights. And then we simplify this. So I'm going to have -2 plus 6 is 4. And then -3 times -2 is 6, plus 3 is 9. And 1 times -2 is -2, plus 18 is 16. So you get 4, 9, 16. All right, so in my second method, that's where I like to know the dimensions of the answer before I start. I know my answer is going to be a 3 by 1 matrix, 3 rows, 1 column. So I like to set up the general shape of it. Okay, it's 3 by 1, 3 rows, 1 column. Or think of it as a vector with just 3 entries. All right, then I fill it in. And I'm going to use the 90-degree rotation method. So you look at the first row of your matrix, 1, 2. Imagine, pick it up, turn it 90 degrees, and put it on top of the -2, 3. The things that line up, you multiply, and you add them together. So you have 1 times -2 plus 2 times 3. And then you go to the second row of the matrix and do the same thing. So the -3, 1, you dot product with -2, 3. So you have -3 times -2 plus 1 times 3. And then you do it for the third row. 1, 6 dotted with -2, 3. So you have 1 times -2 plus 6 times 3. And when you simplify this, you get 4, 9, 16. Any remaining confusion multiplying a matrix times a vector? You'll have some practice in the activities. Call me over if you're stuck. All right, so we have another one. This one's a little different, just in that my vector is a vector of unknowns rather than numbers. But it works exactly the same. So I'm going to do it 2 different ways. The first way says just take each column of the matrix We're going to take a linear combination of those three columns using x1, x2, and x3 as the weights. So I'm going to have 1, 1, negative 3 with a weight of x1, 3, 5, negative 7 with a weight of x2, and negative 4, 2, 6 with a weight of x3. And then I could simplify it if I want to. That's pretty simple already, but this says x1 plus 3x2 minus 4x3, just like read across. And x1 plus 5x2 plus 2x3, and negative 3x1 minus 7x2 plus 6x3. So that's the way the book has shown you. There's another way, which is the row dot product with the column. So with this one, I find it helpful to think about dimensions first. This first matrix is 3 by 3. This vector is a 3 by 1. The inner dimensions match, which means I'm allowed to multiply. The answer is going to be the outer dimensions, 3 by 1. So I kind of build what this is going to look like. 3 rows, 1 column, vector with 3 entries. And then you go row by row, dot product, taking the dot product with the vector x1, x2, x3. So take 1, 3, negative 4, pick it up, rotate it, put it on top of x1, x2, x3. The stuff that lines up, multiply, and then add it all up. So you have 1x1 plus 3x2 minus 4x3. And then move to the next row, 1x1 plus 5x2 plus 2x3. And the last row, dot product with the vector, and you get negative 3x1 minus 7x2 plus 6x3. That's the same thing as I got right here. Okay, so here are many questions that all mean the same thing. They all mean the same thing just because they use vocabulary words that we've been learning that are like synonymous. Okay. Linear combination and span, really closely related, right? Is 4, 12, 4 a linear combination of 2, 1, negative 3, and 6, 5, negative 7? Same thing as asking, is 4, 12, 4 in the span of 2, 1, negative 3, and 6, 5, negative 7? Because the span of a set of vectors is the set of all linear combinations of those two vectors. So asking if 4, 12, 4 is a linear combination is the same thing as asking, is it one of the many linear combinations possible? And then there's a geometric way of asking the question, is 4, 12, 4 in the same plane as 2, 1, negative 3, and 6, 5, 7, if we're thinking about R3, 3D space. Another way of asking this same question is there a solution to this system of linear equations? Okay. Is there a solution to this vector equation? Is there a solution to this matrix equation? These are all the same question as the first three. Right? Because if I'm asking this, I'm asking, are there weights, x1 and x2, that I can put on these two vectors to create this third vector? And that's the vector equation. And then you can translate that vector equation to a system of linear equations or a matrix equation. Here I've used the word span again, but instead of saying the span of two vectors, right? Now I'm saying, is it in the span of the columns, right? Because each column of a matrix is its own vector. Here, linear combination again. Is 4, 12, 4 a linear combination of the columns? Because each column can be thought of as its own vector. So that's a lot of ways of asking the same question. How do you answer all of them? What's that? The same way, yeah. What do you do? Augmented matrix and row reduce. RREF. All right, here's a really important theorem from the reading. It says that if you have an M by N matrix, all of these statements are logically equivalent. That means if they're either all true or all false. So if I were to ask you about the matrix equation having a solution, right? If that question is hard to answer, you could look at any of the other 3 bullets, and if the answer is true, then it's true for the first one. It's false for the first one. Right? So these are either all true or all false. So if I ask you a question that's too hard to answer, you can just answer an equivalent question and know that the answer is the same. All right, so it says the matrix equation AX equals B has a solution no matter what B you choose. Right, so remember that X and B are vectors here. So B is actually like B1, B2, B3, column vector. No matter what vector I choose for B1, B2, B3, there is a solution to the matrix equation. If that's true, they're all true. If that's false, they're all false. Every column vector B can be expressed as a linear combination of the columns of A. The columns of A span Rm. So spanning a space, that means when you look at the span of Rm, the span of the columns, all the linear combinations of the columns creates all of Rm, right? Creates the entire space. We'll do an example that'll make that clearer. And A has a pivot in every row. This is usually the easiest to answer. So if I ask you one of these 3 and it's like, ooh, I'm a little jumbled about what those mean. Does A have a pivot in every row? You can answer real quickly by doing the row reduction algorithm on A, and then you know the answer to any of the other 3. And we'll go through why these are logically equivalent with our example. All right, so I've got a matrix A. It's 3 by 4, 3 rows, 4 columns. So if I wanted to ask the question, do the columns of A span R blank, right? It's only sensible for what number in the box. So let's work this out. The span of the columns of A means all the linear combinations of the columns of A. So that means I'm going to take the columns of A, put weights on them, and add them together. So when I put weights on the columns and add them together, what space does the answer live in? R what? R3. It's going to have 3 entries. So if I ask, do the columns of A span R something, it would have to be R3. Yes. Why? So basically the span of the columns, right? Columns of A spanning, right? The span of the columns lives in R3, okay? Because when I take linear combinations of the columns, I'm always going to get 3 entry vectors as a result. So my question is, can I get any 3 entry vector from all of R3? Can I create, by taking a linear combination of these 4 columns, can I create any vector in R3 I want? Like, you give me a vector in R3. Pick one. Randomly pick a vector in R3. Any 3 entry vector you want. 2, 3, 5. Okay, so if the columns of A span R3, that means that any vector you give me, like 2, 3, 5, I can say, yeah, I can build 2, 3, 5 by taking a linear combination of these 4 columns. I can find weights to put on those 4 columns so that when I add them all up, I get 2, 3, 5. If I can do that for any vector that somebody gives me, like Patrick might give me 7, 8, 9, right? Yeah, I can build 7, 8, 9. I can find weights that I would put on those 4 vectors, add them up, and get 7, 8, 9. If you can do that for every single vector in R3, you say that the columns span R3. They generate all of R3 by taking linear combinations.
Do you have tests?
Yeah, you can't just randomly, you can't just keep testing vectors in R3. So that's what we're going to do here. We're going to answer this question. Does it span all of R3? So it says, express this question. Do the columns of A span R3 using the first bullet from the theorem? So the first bullet from the theorem says, the matrix equation AX equals B has a solution no matter what B you pick. Okay. So my equation is 1, 2, 0, 1, 2, 0, 1, 3, negative 1, 0, 0, 1. My unknown weights, there's got to be some weights that I put on these 4 columns. How many weights do I have to put in this vector? I heard somebody say it. 4, yeah. Because I need 1 for each of the columns. So you take a linear combination of 4 columns, you need 4 weights. x1, x2, x3, x4 equals. And when I take linear combinations of the 4 columns, how big is the resulting vector going to be? Three by 1.
Oh, right, yeah.
Yep, I'm going to take each of my columns in the matrix, put one of these weights on it, add them together. So I'm going to be adding together 3 entry vectors. My answer is going to have 3 entries. I don't know what it is. We'll call it B1, B2, B3. Okay. The question is, does this have a solution no matter what I choose for B1, B2, and B3? Solution for every B. That symbol looks like a V, an upside down A, means for every possible B. Yeah, Justin.
So we're like really tall.
Uh-huh. No. With rows, you can, but not with columns. Yeah. All right, so if I want to express this same question using the second bullet from question 5, from the theorem, part 5. All right, so the second bullet says every column vector B can be expressed as a linear combination of the columns of A. So that means take a linear combination of the columns of A. We don't know what the weights are yet. So the second bullet said in words, it said every column vector B, no matter what you pick for B, you can create it by taking a linear combination of the columns of A. We just don't know what the weights are yet. We would have to solve for them. Okay. Answer this question, right? I want to know, is it possible for every single B, no matter what I pick, to find those weights, x1, x2, x3, and x4? I wrote x3 twice. So I'm going to use my algorithm, use my row reducing algorithm. I'm going to, instead of writing this as a vector equation, I'm going to write it as an augmented matrix. Augmented with we do not know B1, B2, and B3, this needs to have a solution no matter what I pick for B1, B2, and B3, so I'm leaving them generic. I'm going to save us some tedium here. I did this ahead of time. So I did the whole row reduction algorithm, and I get 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1. And this is B1, negative 2B1 plus B2, and negative 2B1 plus B2 plus B3. So what do you think? Is there a solution? Why not? I see a pivot in row 2. I see a pivot in row 1. There's a pivot in all 3. Yep. Rather than thinking about pivots, though, last class when we found some inconsistent systems, what was the thing that you'd see when an inconsistent system? 0 equaling a number, right? Do any of these rows say 0 equals a number? No. So this is okay. We have a solution. 1 free variable. Yeah. Which one is it? X2. Yeah. The column, because this column represents X1. These are coefficients on X1, coefficients on X2. So the X2 column has no pivot in it. Yeah. So maybe that's why somebody said there's no pivot in row 2. I think you meant column 2. Yeah. Yep. I think I just stopped once it was in echelon form, and I didn't do the backwards phase. Yeah, I didn't do the backwards phase just because I didn't need to. I think I was once I had it in triangular form, then I said, okay, I've got pivot, 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 the leading entry of each row, and that tells me there is a solution. I didn't care what the solution was. I was just trying to find out, is there one? So because in none of my rows do I get 0 equals a number, yes, there's a solution. There exists a solution for every possible B. Backwards capital E means there exists. Yes. Not necessarily. You might, there may or may not be a solution. Yeah, I don't think you can generalize. All right, so this question we should be able to answer really fast now. Is 1, 2, 7 a linear combination of the columns of A? Yes, because no matter what I pick for this 3-entry vector, we'll always be able to write it as a linear combination of the columns of A, because I just showed that for a generic B1, B2, B3, there's a solution. There's a way to write it as a linear combination. So this is a yes. Right, so that's it. Got a good 22 minutes to start the activities for this lesson.